least 10 to 100 times harder to do the factory than the prototype. And that's why you see a lot of companies out there, or startups, just software in general. These are fundamental. These are the 3 critical areas that are needed to make for an awesome company. So, yeah. So we have, now we'll soon have 3 new factories, incremental, on, well, we have one already, on 3 different continents. Shanghai, we're expanding to Shanghai with the 2nd phase. Berlin is making rapid progress, and Texas is making even faster progress. So, yeah. With each, so in terms of Tesla's contribution, we've delivered over 1 million electric vehicles, 26 billion electric miles driven, and many gigawatt hours of stationary batteries, 17 terawatt hours of solar generation. To sustainable energy, we must produce more EVs that need to be affordable, and a lot more energy storage, while building factories faster and with far less investment. So, goal number 1 is a terawatt-hour scale battery production. So, Tera is the new Giga, and a terawatt is 1,000 times more than a gigawatt. So, we used to talk in terms of gigawatts. In the future, we'll be talking in terms of terawatt hours. So, this is what's needed in order to transition the world to sustainability.
And now we do this for batteries as well. We have a plan to halve the cost per kilowatt hour.
Yeah.
And it's not a plan that rests on a single innovation, some research project that'll never see the light of day. It's a plan that has taken creative engineering and industrialization across every facet of what makes a cell into a battery pack, from raw material to the finished thing. And we're going to go through that plan with you today, step by step, and build up how we get to these goals and how we accelerate this transition and make our vehicles and our grid batteries more affordable.
Yeah, I mean,
we came up with this tabless architecture that may be form factor and the simplest manufacturing process. And this is what we mean when we talk about tabless. It's kind of a beautiful thing.
Yeah, that's what these T-shirts mean, but it's very esoteric. It's like nobody could figure it out. But
yeah, we basically took the existing foils, laser patterned them, and enabled dozens of connections into the active material through this shingled spiral you can see, with simpler manufacturing, fewer parts, 50 millimeter versus 250 millimeter electrical path length, which is how we get all the thermal benefits.
Yeah, this is important to appreciate. Like basically, the cell is bigger. It actually has more power. The power to weight ratio is actually better than the smaller cell with tabs. This is, again, like this is quite hard to do. So it's, nobody's done it before. And it really took a tremendous amount of effort within Tesla engineering to figure out how do we make a freaking tabless cell and have it actually work and then connect that to the top cap. And it's there's a whole bunch of things that were, just to elaborate on that a bit. It's like when the cell is going through the system, it has to keep stopping where all the tabs are.
Yes.
So you can't do continuous motion production if you have tabs. You have to keep stopping, and then there's a rate at which you can start and stop and accelerate again, and it really slows down the rate of production. And then sometimes you get the tabs wrong, and you also lose a little bit of active area. It's really a huge pain in the ass to have tabs
Yes.
from a production standpoint.
Yes. And so when we put it all together and go to our new 80 millimeter length, 4680, we call this new cell design, we get 5 times the energy with 6 times the power and enable 16% range increase, just form factor alone.
Yeah, so when
Concept or a rendering, we are starting to ramp up manufacturing of these cells at our pilot 10 gigawatt hour production facility just around the corner.
Yeah. So, yeah. It's a video of some of what's going on in the plant. Now, I mean, to be clear, it will take about a year to reach the 10 gigawatt hour capacity. So,
Thank you. um, but let's stack up everything we just saw at the cell level. So just the cell form factor change enables a 14% dollar per kilowatt hour reduction, just that cell form factor change. And now that you've been teased on this factory kind of things where you put the solvent in and then take it out and recycle it, and just go straight to dry mix to coat. And that's what the dry process really is about. Yeah, but if you do scale it up,
yeah,
what you saw before becomes this.
Yeah.
So you can see the motivation. A 10 times reduction in footprint, a 10 times reduction in energy, and a massive reduction in investment. But as Elon was saying, simple is hard.
Yeah. Yeah, I mean, to be clear, I would like to not say that right now it's just totally working. It's close to working, but it's not, even now, at the pilot plant level, it is close to working. Well, it's fair to say it does work, but with not a high yield.
Yeah.
So
we're still ironing out the kinks, but we've made tens of thousands of cells, thousands of kilometers of electrode. I mean, we are on the 4th generation of the equipment, so we've learned a lot along the way.
Yeah.
I mean, it is super demanding because every atom has its place if you want to deliver the energy density and the cycle life and the supercharging.
Yeah.
But we're confident that we will get there, but it will be a lot of work along the way.
There's a clear path to success, but a ton of work between here and there.
Yep.
So
the key to a high-performing assembly line is accomplishing processes while in motion, continuous motion, and thinking of the line as a highway, max velocity down the highway, no start and stop, no city driving.
Exactly, no stoplights and traffic lights or anything. You want the highway.
I want the highway.
Yeah.
And together with our internal design team that makes this equipment and designs this equipment, we coupled thinking about how to make the best cell with thinking about how to make the best equipment so that we could accomplish the fastest parts per minute rates on all of these tools. And through all of that development, we were able to get to the point where we can implement assembly lines, one line, 20 gigawatt hours, 7 times increase in output per line. And when you're thinking about scalability and pure effort, having one line be 7x the capability is just effort multiplying.
Yeah. So,
only the value added represents 25% of the investment. And what is formation? It's charging and discharging cells and verifying the quality of the cell. Turns out we've charged and discharged billions and billions of cells in our vehicles, so we know a thing or two about that. The typical formation setup is you charge and discharge each cell individually. In our car, we charge thousands of cells at once. And we took our principle and our power electronics, leveraging Powerwall, vehicle battery management systems, and others, to dramatically improve the formation equipment cost effectiveness and density. 86% reduction in formation investment, 75% reduction in footprint.
essentially, what this translates to, based on what we know today, is about a 75% reduction in the investment per kilowatt hour or gigawatt hour. It's just basically 4 times better than the current state of the art, to the best of our knowledge. And I think there's probably room to improve even beyond that.
Definitely.
Definitely, yeah. So you can see, like, basically, we can get a terawatt hour in less space than it took to make a gigawatt hour. 150 gigawatt hours. So this is pretty profound. It's like I would actually not have thought this was possible several years ago. That we could actually get to terawatt hour scale in less space than what we currently envision for doing 150 gigawatt hours.
Yes, simpler accelerates terawatt hour scale, and that's what we need to do to accelerate our mission.
Or 3 terawatt hours per year. I think I think we've got a good chance of achieving this actually before 2030, but I'm highly confident that we could do it by 2030.
When you look at the size of that manufacturing innovation, fantastic for enabling scale. It's also an additional 18% reduction in dollar per kilowatt hour at the battery pack level. What are the active materials we're going to put in that cell design? Let's talk about the anode first. Let's talk about silicon. Why is silicon awesome? It's awesome because it's the most abundant element in the Earth's crust after oxygen, which means it's everywhere. It's sand.
Yeah. Sand is silicon dioxide.
Yeah. And it happens to store 9 times more lithium than graphite, which is the typical anode material in lithium-ion batteries today. So it expands 4x when fully charged with lithium. And basically, all of that expansion stress on the particles start cracking, they start electrically isolating, you lose capacity, the energy retention of the battery starts to fade, and it also gums up with a passivation layer that has to keep reforming as the particles expand.
Yeah, basically,
in the cars that you're all in right now,
so in order to scale, we really need to make sure that we're not constrained by total nickel availability. I actually spoke with the CEOs of the biggest mining companies in the world and said, please make more nickel. It's very important. And so I think they are going to make more nickel. But there's also, I think we need to have a kind of a three-tiered approach to batteries. So starting with iron, that's kind of like a medium range, and then nickel manganese as sort of a medium plus, intermediate, and then a high nickel for long range applications like Cybertruck and the semi. Something like a semi truck, it's extremely important to have high energy density in order to get long range. So it starts with having a single piece casting, or a single piece casting for the front body and the rear body. And in order to do this, we commissioned the largest casting machine that has ever been made, and it's currently working just over the road at our Fremont plant. We have it's pretty sweet. Currently making the entire rear section of the car as a single piece, high pressure die cast aluminum. And in order to do this, we actually had to develop our own alloy. Because we wanted a high-strength casting alloy that did not require coatings or heat treatment. This is a big deal for castings, especially with a large casting. If you heat treat it afterwards, it tends to deform. It kind of like does this like potato chip thing. So it's very hard to keep a large casting to have its shape. So in order to achieve this, there was no alloy that existed that could do this. So we developed our own alloy, a special alloy of aluminum that has high strength without heat treat and is very castable. So that's a great achievement of our materials team. In fact, in general, we've got a lot of advanced interfaces to what we call the structural battery, where the battery for the first time will have dual use. The battery will both have the use as an energy device and as structure. This is really quite profound. Effectively, the non-cell portion of the battery has negative mass. So we save so much mass in the rest of the vehicle. We save more mass in the rest of the vehicle than the non-cell portion of the battery. So it's like, well, how do you really minimize the mass of a battery? Make it negative. Make the battery non-cell portion of the battery pack negative. It also allows us to pack the cells more densely because we do not have intermediate structure in the battery pack. So instead of having these like supports and stabilizers and stringers and structural elements in the battery, we now have a lot more space in the battery because the pack itself is structural. And what we do is essentially, instead of having just a filler that is a flame retardant, which is currently what is in the 3-in-Y battery packs, we have a filler that is a structural adhesive, as well as flame retardant. So it effectively glues the cells to the top and bottom sheet. And this allows you to do shear transfer between the upper and lower sheet. Just like those castings are also quite important because you want to transfer load into the structural battery pack in a very smooth, continuous way, so you don't put arbitrary point loads into the battery. So you kind of have to, you want to sort of feather the load out from the front and rear into the structural battery. It also allows us to to move the cells closer to the center of the car. Because we don't have the in the top one, we've got that sort of all the supports and stuff. So the volumetric efficiency of the structural pack is much better than a non-structural pack. And we actually bring the cells closer to the center. Because they're closer to the center, it reduces the probability of a side impact potentially contacting the cells, because it has to go, any kind of side impact has to go further in order to reach the cells. It also improves what's called the polar moment of inertia, which is that you can think of like when there's ice skater, arms out or arms in. Arms in, you rotate faster. So if you can bring things closer to the center, you reduce the polar moment of inertia, and that means the car maneuvers better. It just feels better. You don't want to know why, but it just feels more agile. So it's really cool. This is really major. Like I said, so 10% mass reduction in the body of the car, 14% range increase, 370 fewer parts. So
35% reduction in floor space, and we'll continue to improve that as we make the vehicle factory of the future.
yeah, so it's major improvements on all fronts, from the cell all the way to the vehicle.
And in addition to the improvements we just said on enabling additional range and improving the structural performance of the vehicle, it is worth another 7% dollar per kilowatt hour reduction at the battery pack level, bringing our total reductions now to 56% dollars per kilowatt hour.
Yeah.
Not just talking about cost or range, we've got to look at all the facets. So range increase, we're unlocking up to 54% increase in range for our vehicles and energy density for our energy products. 56% reduction in dollars per kilowatt hour at the battery.
Sustainable energy products that we make will be massively increased. So, what tends to happen as companies get bigger is things tend to slow down. Well, actually, they're going to speed up. About 2 billion vehicles. So long term, we want to try to make about 20 million vehicles a year.
But I think it's important to point out that when we talked about 3 terawatt hours by 2030, the problem is a 20 terawatt hour problem. So everybody needs to be accelerating their efforts to accomplish these objectives. Doesn't matter.
What does this mean for our future products? We're confident that long term we can design and manufacture a compelling $25,000 electric vehicle. This has always been our dream from the beginning of the company. I even wrote a blog piece about it because our first car was an expensive sports car, and then it was like slightly less expensive sedan, and then finally sort of a mass market premium, but like the Model 3 and Model Y. But it was always our goal to try to make an affordable electric car, and I think probably, like I said, about 3 years from now, we're confident we can make a very compelling $25,000 electric vehicle that's also fully autonomous.
And when you think about...
what about that? Yeah. Woo. So, we took the latest Plaid out to Laguna Seca on Sunday. It got a minute 30, and we think probably there's another 3 seconds or more to take off that time. So we're confident the Model S Plaid will achieve the best track time of any production vehicle ever, of any kind, two-door or otherwise. And you can order it now, and it's available basically end of next year.